Okay, now let's, since we discussed this transition, now let's move on to more quantitative stuff. So, before explaining the methodology for solving a turbulence flow, we have to discuss about something called energy transfer in turbulence, or energy cascade. What this is basically breaking down and explaining the flow of energy from start to end of a turbulence flow, meaning how the energy is supplied, how the energy is being transferred inside a turbulent flow, up to how it's going to be dissipated. So this is called basically energy cascade. So what happens is basically, if we want to explain it very simply, the energy is being supplied to the large scale eddies. So these are large structures you see on the picture in here. This is actually a picture of an experiment. So the energy is supplied to the large scale eddies. How do we supply energy to large scale eddies? Through our velocity, inlet velocity. So that's the source of our energy, the kinetic energy that is pushing the flow forward, which could be from a compressor, which could be from a pump, etc. Right? Then energy from these large scale eddies will be transferred to medium sized eddies, which are in the middle of the flow, and from those to the small eddies. So these small eddies are so small that due to the friction to the surrounding air or surrounding wall, they're going to basically convert the energy into heat and waste it. So that's how the energy system works in a turbulent flow. So do you supply the energy to the large ones, and it's being dissipated through the small eddies. Now, if the amount of energy you are supplying to the large eddies is equal to the dissipation from the walls, you're going to have a turbulence flow which is not changing in its state, meaning it's not dying out, it's not increasing in turbulence. If your supply of energy is more than your dissipation, you are creating more and more turbulence. And if your supply of energy is lower than your dissipation of energy, what happens is your system is going to eventually, your turbulence is going to eventually die out, and the flow becomes a laminar flow. Now, let's look at that energy cascade from other aspect. If we basically plot the energy based on wave number, and the wave number is basically the inverse of your wavelengths. So wave number is the inverse of wavelengths, meaning small eddies which have small wavelengths, they have large wave numbers. So as on the wave number axis, as I'm moving toward larger wave numbers, meaning I'm moving toward smaller eddies. Now, the energy of those eddies looks like this. So, integral scale are the large eddies, Taylor scale are the medium eddies, and Kolmogorov scale are the small eddies. And this is how the energy is being distributed in here. Most of the energy, of course, is in large eddies, and Taylor scales are less amount of energy. And as we go to the Kolmogorov scales, they have even less energy. Now, in this graph, since we know the energy is supplied in here and dissipated in here, meaning supplied in integral scales and dissipated in Kolmogorov scale, we are defining three parameters. One is called kinematic viscosity, which you know, which is the inverse of viscosity, right? Density over viscosity, right? Viscosity over density, which is called kinematic viscosity. Then you have K, which is the turbulent kinetic energy. K is the amount of energy you are supplying to the system. So that's your turbulent kinetic energy. Then you have epsilon, which is your dissipation rate. So in a turbulent flow, it is always and always a competition between K and epsilon. And you will see these K and epsilon parameters showing up in our models, which are used to solve turbulent flow. So K is this energy supply, epsilon is the energy dissipation. Now, our objectives to solve and simulate a turbulent flow is as follows. We will try to capture the spectrum as much as possible, because remember, we told you're dealing with a wide range of length scale, from micron size eddies to very large eddies. So whatever model we use, we will try to capture as much as possible from large and small, to both ends of the extreme. We will try to develop equations to predict the time average velocity, pressure, and temperature. We will do so without calculating the complete turbulent flow pattern as a function of time. You might think, okay, didn't we say that turbulent flow is inherently transient, is inherently unsteady? Now, the method we are using is called time averaged, and we want to solve for averaged values. Yes, we want to do that because, remember, going back to what we explained in our first session, there are two ways of going around a CFD problem. One is called direct numerical simulation, which means you don't use any model, you don't use any auxiliary equation, you just go and solve our 5 main equations, which are 3 velocities, 1 temperature, and 1 pressure, 1 continuity. But to do so, you require insanely refined mesh, which increases your calculation time and calculation capacity enormously, couple of order of magnitudes higher than what it should be. Right? If you have a supercomputer, if you have enough time, by all means do that. If you do so, all you need to take care of are those 5 equations. You don't even need to know whether, of course, before simulation, you don't need to know whether the flow is turbulent or laminar. You don't need to know anything, because those 5 equations are the basic equations, and if you solve them properly, they're gonna give you the results regardless. Okay, so that's that. But for us, since we don't have a supercomputer, since we want to solve it faster for practical industrial reasons, we can't go around having insanely refined mesh. So what we do is we use auxiliary equations. You remember that? So this is basically in that part. Turbulence is a very difficult problem, so we use time averaging as auxiliary equations to be able to solve the problem. So the prediction methods, before diving into the prediction methods, individual prediction methods, let's have a bigger picture of them. So if this is your energy flow, right, your energy cascade, you provide energy to the larger scale eddies, they flow through medium size eddies or Taylor scale eddies, then they dissipate, then the energy is dissipated through small eddies, right? This is what we had. If you use DNS, which means direct numerical simulation, you will be able to resolve from the large eddies to the small eddies, meaning you don't use any sort of auxiliary equations or modeling. You just use 5 equations and solve this. If you use a method called large eddy simulation, you will resolve up to the medium-sized eddies, meaning you will use your basic equations to solve them, but for small eddies you will use modeling, meaning auxiliary equations. If you use Reynolds average Navier-Stokes equations, or RANS, you are only resolving, meaning you are only using 5 basic equations for the large eddies. The rest is modeled through auxiliary equations. And these 3 are basically the main categories. There are different methods under each category, but this is the main. So when we say we are using a RANS model, you got to remember, okay, we are just basically really solving the large eddies. The others are being modeled. Okay, so remember that. Now, since in this class we're gonna focus on RANS models, and to be honest, 99% of the problems in industry are being solved with RANS models, so we're gonna focus on that. If you remember, in RANS models, I said you are taking a time averaged velocities, right? Meaning you're solving it all together as a steady flow. So what's gonna happen? Now this is an example showing basically a difference. This is a flow over a step. So this is your step, this is a flow over it. If you solve it, say, using DNS, which resolves everything, this is what you're gonna see of different velocities. Lower velocities in blue, medium velocities in green, higher velocities in red and pink, right? Now if you use time average velocities, still you're solving a turbulent flow, you're gonna see this. Yeah, sure, you don't see the fluctuations, but you pretty much have predicted very well where the lower velocities are, where the medium velocities are, and where the high velocities are. And that's all matters in industry. That's all matters in many practical simulations, because you do not have any use for these fluctuations. All you want to know, okay, I'm going to solve this turbulent, but I want to know where are the large, small, medium-sized velocities, right? That's why we use time average velocity contours. Now, let's see what the RANS model is. In mathematics, you can time average any parameter, any arbitrary parameter can be timed averaged using equation as this. So you take a parameter f, you time average it over time, meaning you integrate it in a period of time, then divided by its period. That becomes time averaging. That takes the fluctuations out of it. Now, we're going to use this equation, right, to solve for our turbulence flow. So what we're going to do is, first, if you remember, I told you we will decompose all our parameters to an average parameter plus the fluctuation part. So the P bar and U bar are the averaged, which means there is no fluctuations, and of course plus P prime and U prime, which are the fluctuations. Now, what we're going to do is we're going to take every equation we have, meaning the continuity equation and the Navier-Stokes equation. Guys, please listen very carefully here, because this step is not included in this slide. So you will take the continuity equation and you will take Navier-Stokes equation. First, you will substitute all the PU parameters with this decomposition, with P prime plus P bar, U prime plus U bar. Once you did that, you will apply this averaging equation to those. If you follow this procedure, this is going to be your final result for your continuity. So in continuity, as you see, by decomposing and averaging, we have been able to get rid of all the fluctuation parameters, and continuity is just in terms of the average velocities, which we will go about solving it as usual. So there is no fluctuations. And the purpose of this method was getting rid of the fluctuations. Okay. Now, if we do the same, to the Navier-Stokes equation, meaning substituting the parameters with the decomposed versions of them, then average them, every parameter, as you see here, would be in terms of average velocities, right, and average pressures, except the last one, except this parameter, which is still remain in terms of the ui primes and uj primes, in terms of the fluctuations. If we didn't have this parameter, the job was done. We could have solved these two together as usual, meaning solving our continuity and Navier-Stokes equation without the presence of the fluctuations, and we were done. But still we have this one, and we have to figure it out because u primes are unknown, so we have to come up with something for this parameter. This parameter, which is called Reynolds stress tensor, is actually a tensor like this, because remember, you're talking about three equations, right? Three velocity equations in each direction, so that's why you have three tensors of it, right? So, but we have to come up with something because we don't want to add new unknowns to the system. These are all unknowns, so we have to do something about it. So what we do is called actually the closure problem, meaning we have to get rid of these extra unknowns to close our problems, meaning to get rid of the extra parameters in our equations, because remember, we only have 5 equations and we have only 5 unknowns already, so you don't want to add new unknowns to the system. You use something called eddy viscosity models. So based on the Bosnisk, and this is the same guy but not the same theory, based on the Bosnisk hypothesis, you can write down the Reynolds stress by a combination of the derivatives of the average velocities. So this was the parameter we wanted to get rid of, right? This was the parameter in here. We wanted to get rid of this. So we will get rid of that by substituting it with a combination of average derivative of average velocities multiplied by something called eddy viscosity or turbulent viscosity, mu t. This mu t is a new parameter, it's a new coefficient, is a totally man-made artificial equation. Now, by substituting this with this, we have partially solved our problem, meaning we have gotten rid of primes and everything is in terms of average velocities again, but still we have an unknown. We have introduced a new unknown, mu t. So we have to do something about this. So from here, we reduced it to this, and now we have to get rid of mu t. So this is the mu t. The unit for mu t or turbulent viscosity is same as molecular viscosity, is Pascal seconds. Okay, so remember, it's also called eddy viscosity, and you can also define kinematic turbulent viscosity mu t, nu t, which is mu t divided by density. Okay, and so now let's look at how we can go around and find something for mu t. Now, up to this point, all the RANS models have the same logic. This is the logic up to this point for all the RANS models. They do not differ in anything up to this point. But from this point on, depending on how they calculate mu t, they will differ. So all these are the RANS based models, but they differ in the way they calculate mu t. Some of them uses one equation, some of them two equations, so on and so forth to calculate mu t. And as we increase the number of equations, it becomes more accurate, but of course heavier in simulation.